It's a great pleasure to start our in-person colloquia with Professor Clifford Johnson from University of Southern California. The theorists among you may know him from Notes on Deep Brains, the lectures from which many of us learned about deep brains many years ago. He has many other achievements. As to his name, he received his BA from Imperial College and then a PhD from Southampton University. Had several visiting postdoctoral positions at prestigious institutions, KITP at Santa Barbara, Institute for Advanced Studies, Princeton. Professor Johnson is currently on sabbatical at the Institute for Advanced Studies. He received a career award from the NSF in 1997, the Maxwell Medal from the Institute of Physics in 2005, and a Simons Fellowship in 2016, and he's a fellow of the American Physical Society. Besides the institutional aspects of his work and his research, he has been present on the wider media. He gave TED Talks. He is a regular in the History Channel program on the universe, and he has been a consultant for the Discovery Channel. I understand also that Professor Johnson has various books already published. The most recent one is actually a physics and modern physics-based graphic novel called Dialogues. I'm very happy to have Professor Johnson here and to be able to have this talk in person. He will talk about black holes, quantum gravity, and random matrices.
Thank you very much for the invitation. I hope everyone can hear me and see the screen. Unfortunately, the pointer I was hoping to use, in which I could write detailed responses to any questions and do calculations for you live, doesn't seem to be working, but I'll do my best with the good old-fashioned mouse pointer, which I think is visible. So without further ado then, I will start. And first of all, just say it's a really exciting time to be in this area of physics because there's so much intersection with several other areas of physics and also, of course, with for sure, experiment and observation in the following sense. We've gone very rapidly from talking about black holes as interesting and weird solutions to Einstein's equations to thinking about that they must be inevitable but may be hard to see, to now, studying collisions of them routinely through the gravitational wave emissions that are now being detected by, for example, LIGO and Virgo. I'm showing you here a plot of, which is already out of date, of many of the various black hole mergers that have been observed since those experiments started. And of course, we're also taking pictures of them using essentially the entire planet Earth, the network of radio telescopes called the Event Horizon Telescope collaboration, being able to actually come up with imagery of the supermassive black holes. And you have these other kinds of black holes colliding. And the lesson seems to be that we're in this exciting time where black holes are now all around us, which many people suspected. They're in a range of shapes and sizes. And in fact, that then gets a lot of theorists excited who've been thinking about issues in quantum gravity, because, well, as soon as you have black holes, you must confront that with our poor understanding of how gravity works at the quantum level. But you can really make very sharp statements, at least for small black holes. Those corrections we expect from quantum gravity must be very large, and we cannot ignore them. What we learn about those sorts of physical processes will teach us about things that we also know are urgent to understand in the larger scale cosmology. Trying to understand the early universe will also force you to confront your understanding of quantum gravity. So what is quantum gravity? And the answer is, well, we're not sure what nature's quantum gravity actually is, but when we think about what we know about gravity and what we know about quantum physics, we can make some guesses about what we should expect. So first of all, gravity is the dynamics of space-time, and quantum physics tells us that we must sum over such dynamical possibilities to get answers. And so putting them together is the thing we ought to do. And the question is how? How do we sum over space-time, if that's what we're supposed to do? And what does it teach us if we can do it? So what I'd like to tell you about today is that there are areas, some of which you've already heard of, concerning being able to do that in controlled models. But some of the exciting things I've been having recently is, I think, getting closer to understanding a lot of questions about dynamics, at least in a number of cases. And those cases, I think, are generic enough to tell us with some assurance that we're seeing some features that should be true. And it's of course possible that we're still completely wrong, and one day we'll find that nature is described by a quantum theory of gravity that there's something completely different. But until then, you use what you can in order to constrain what we might see. And the first pass at doing quantum gravity, of course, goes back to the pictures we've all seen, where we look at the two starkly different things that are going on in the main theories. You have, on the one hand, Einstein's theory telling you that you have horizons, which are a locus of points that separates, in a definite sense, the inside from the outside, the horizon of a black hole, for example. On the other hand, we have from quantum theory that we have this the seething possibility in the vacuum, the possibility of having, for example, pair creation, telling you that everywhere there's some probability that you will produce a pair of particles which will exist for some time and then disappear. And if you try and put these things together, they're not going to agree with each other. Something must change. And in fact, that was one of the computations that made Hawking very famous. The realization that, for example, if this happens near a black hole, then you will indeed have the possibility where one of those virtual pairs goes behind the horizon and is lost forever, it would seem. And the other one would then fly free and be measured to an observer as an emission from the black hole. If you do the computation fully, you'll see that, in fact, the thing going in reduces the mass of the black hole. And so the black hole is apparently radiating due to quantum physics. When you do the arithmetic in the semi-classical limit, where essentially you treat space-time as a background on which you do quantum field theory, you actually arrive at the striking conclusion that the black hole actually behaves as though it has a temperature. In the case of a simple Schwarzschild black hole, the temperature goes inversely with the mass. And indeed, as Bekenstein argued and showed by combining that with other work on the dynamics of black holes, the black hole's entropy as a thermodynamic object is in fact proportional to its area, the area of the horizon that surrounds it, divided by 4. And I've been the usual annoying theorist that has set dimensional constants, all the various constants of nature, which should be in here, to 1. In particular, there should be G Newton down here, and with M here, and there's an H bar telling you that these are quantum results, and various powers of C to get the dimensions correct. And if you want, you could also throw in Boltzmann's constant. But anyway, I've set all of those to 1. So those, but the 4 I will not set to 1, because the 4 is actually important. It's not from dimensional analysis. So, continuing this first pass at how we might do quantum gravity, Gibbons and Hawking showed that a nice way of putting this all together mimics what we do in other areas of physics, where you can study a theory at finite temperature by working in Euclidean time, which I'm denoting here as tau, which is then periodic with some period beta. And beta is the inverse temperature. And that allows you, for example, in computing the partition function to explore the thermal properties of a theory. Now you do this on the whole space-time with this technology. So if I have the coordinates surrounding a black hole as a point, which is theta and phi, the spherical angles, and then I have radius and time. Radius and time, when I've Euclideanized time, form there's radial variable, and then time is now periodic. And indeed, then I have a problem if I have an arbitrary period for those oh, it's from maybe one of our the audience. If there's an arbitrary period, so the requirement that you don't have a conical singularity, which would invalidate the whole calculation because you have places of high curvature and you're supposed to be working in a nice sort of smoothly curved semi-classical regime where Einstein's equations are true. The requirement that you don't have that sets the period. It essentially says if I take a plane and I don't have period 2 pi for the phi coordinate, I'll have a conical singularity. So the analog of that sets for you a condition on the temperature, that periodicity beta, and that is another way of seeing the result. So you can do this for all kinds of different black holes. And it's actually fun to do that if you want to experiment with those calculations and if you haven't done that before. So there's a result for a charged black hole in flat space and a curved black hole in flat space and so on and so forth. What ends up are the laws of thermodynamics of a black hole, which follow from this and previous work that had been done by various groups telling you about the non-decreasing area of a black hole, which then translates into the non-decreasing entropy, which would be the second law of thermodynamics, and so on and so forth. So a very beautiful subject, even if you're just staying in the semi-classical regime of essentially a background space-time and then looking at quantum fields on that. But we'd like to do more than that. And one of the key things is that, well, if a black hole has entropy, and it's finite, that has consequences. Right? And the consequences are, according to Boltzmann, is that there should be some quantum microstates. This is telling me that I'm counting something. There should be some underlying discrete system that accounts for this entropy. Put a different way, I should have some quantum mechanical Hilbert space whose dimension is essentially set by the entropy. So can we see those degrees of freedom? Because that would be really getting to grips with the guts of the quantum theory of gravity, in the same way that looking at the thermodynamic description of the properties of my glass of water here is something I can do in thermodynamics, but I can also look at the microstates and really get to grips with the molecules and their motions, telling me about the dynamics that's giving rise to these macroscopic observed quantities. So it's the same thing that you'd want to do. This also brings up an important other famous puzzle, which is the black hole information paradox, which is that it would seem that I'm able to throw coherent information, pure states, for example, into a black hole. And if the black hole ultimately radiates away, because it's losing mass, purely thermally, then I've converted pure states into mixed states, which is something that would violate the laws of quantum mechanics. So is that what happens? And well, the answer is, and you may have had talks on this, it would seem that that's no, because of things like ADS-CFT, which I'll remind you of shortly. And there's been some exciting recent work on something that's often just called islands by various groups, which is in various toy models shown in principle how that paradox is avoided by actually keeping track of the entropy of the radiation of the black hole and seeing that you don't run into a refined version of that paradox. And there's a lot of things that I'm going to talk about in what's to come that will also implicitly address that same puzzle. So let's try and be a little bit more careful. Let's try and do a second pass about what we should do if we're trying to understand quantum gravity. It should be more than what we've seen so far. Going back to our picture, we should expect that, in fact, yes, we're summing over not just some fixed geometry, we should perhaps sum over some dynamical geometry, allow the geometry to do things, sum over those possibilities. But we should also even perhaps sum over topology as well, which is something else that the space-time should be able to do. So do we have good models of that? And the answer is yes. And there's been a lot of progress. And again, that's a whole other seminar to tell you about this. But one place where that's very well understood is what's called holography, which is built on the holographic principle that Hooft suggested back in '93, which was amplified and brought in the direction of string theory by Susskind in '94. And it says something very profound. It says, well, if I have quantum gravity in some d-dimensional space-time, it should be equivalent to doing physics in some d-1 dimensional non-gravitational theory. But you can see if you could establish that, then things like the formation and evaporation of a black hole in the full quantum gravity theory should be not actually mysterious at all. It should be perhaps some complicated but manageable, sensible unitary process in this non-gravitational setup. And that is indeed what turns out. You can see it, at least, if not in detail and following a particular black hole, you can see that there are phases where black holes appear and disappear, and they have a description in terms of things that we understand in non-gravitational language through this map. But you might want to get the details, not just some sort of general, in principle, we solve the problem. The details came about because we found, began to come about because we found examples of examples of the holographic principle, this setup in string theory. And in particular, through the 90s, we began to see things like what we were called gauge gravity correspondences, and then it got sharpened by Maldacena, and then soon after by Guxer et al. And by Witten into the ADS-CFT correspondence. And the simplest versions of those that appeared in those first examples look something like this. There are various kinds of extended objects that live in string theory and its strongly coupled extension that's called M theory. And they actually have two descriptions. You can either describe their gravitational footprint on the space-time, which is a gravity kind of process, or you can describe them in terms of a theory that it describes their dynamics completely differently from that in terms of just field theory variables. And in these simple cases, those field theories are actually conformal field theories. And there's a dictionary between these two. You can use one description or the other, and you get the same physics. So that correspondence then looks something like this. Examples include anti-de Sitter spacetimes of various dimensions, 7, 5, 4, 3, etc. And those end up corresponding to 6-dimensional, 4-dimensional, 3-dimensional, 2-dimensional conformal field theories. And you can see the D and the D-1 right there. So one of the really wonderful things about this is that you can say a lot of beautiful detail. So, for example, the ADS-5 version of this story is due to some 4-dimensional theory, which is a Yang-Mills theory, which is great because Yang-Mills theory, nature does like Yang-Mills theories in 4 dimensions. So that's good. And what you find is that there are wonderful things. For example, you have transitions that were studied by Hawking and Page going from 5-dimensional ADS to 5-dimensional ADS with a black hole, what was called the Hawking-Page phase transition. And that ends up being dual, as shown by Witten, to the deconfining phase transition in the gauge theory at finite temperature. And so again, we're seeing examples where black holes can appear and disappear. And in fact, the space-time topology changes. And that's something that's happening as a familiar thing in gauge theory, although hard to compute. So this gives you a way of computing some of these complicated things in gauge theory. So that's what was going on there. You might ask, well, can we use holography then to understand details of the microphysics of the black holes, rather than talking about phases that may or may not contain them? And the answer is yes. It started with Strominger and Vafa being able to compute the entropy of various kinds of black holes and generalizations of that at t equals 0, where you have certain kinds of charged black holes have an entropy at t equals 0. The whole thing has some nice special properties that allow you to embed it into string theory, where you can count the microstates. But you still might go, well, that's nice, and it is nice because you do the counting and you find you get exactly that area over 4, not just area. It goes like the area in some general sense, but you can specifically verify the Bekenstein-Hawking entropy. But you might go, well, yes, fine, but what have you done for me lately? In other words, can you go beyond just the counting and do dynamics at non-zero temperature? And that's what I want to talk about today. But what you need to be able to do, or one way of doing it, is to fill out the rest of the table, because you may have noticed in this table that perhaps the earliest example that you've met, perhaps in a GR class, of some anti-de Sitter times a sphere is in fact the thing that lives at the core of a 4-dimensional charged black hole, ADS2 cross S2. And I'll show you, I'll remind you of that if you missed that that day in GR class. So if I could understand the description of an ADS2 cross S2 spacetime, or what I'll talk about, which is a finite temperature version of that, as some holographic dual theory, then dynamically, then we would have had a little bit of an exciting, I hope you'll agree, answer to this question of getting control of the dynamics. And that's what a lot of people have been working on in one guise or another in recent times. So let me tell you a little bit about that. So indeed, let's go back to GR, write down the Reisen-Norton solution. So now this is not a black hole in some weird space-time. This is in asymptotically flat space-time. That's another reason this is interesting, because we'll be getting insights about the dynamics of quantum gravity in our universe. There are analogs of this discussion that go, for example, to similar in Kerr black holes. A piece of this would show up there as well. And probably all the black holes in our universe are Kerr black holes. So we're getting closer to learning something about quantum gravity in our universe, perhaps. So the extremal solution is when the mass is equal to the charge, and it actually then has t equals 0 if you do the calculations I mentioned before, like Gibbons-Hawking. And you can write a coordinate where the radius that you usually use, little r, is traded in for a capital R, so that when the radius is at the horizon, r goes to 0. If you use that coordinate, you get this sort of space-time. And the coordinates are such that, if you look at it, at large R, this is very small, this term, that term, and that actually then is just flat space-time. So I'm far away from the black hole. At small r, this begins to diverge, and I can throw away the 1, and I get this space-time. It looks like this. And what's happened is that I've gotten this interesting space-time called ADS2 cross S2. You can see the transition between these two regions is as follows. As I go to large R, the spheres, as I do in ordinary 3 dimensions, the spheres grow in size with R as I move out from some point. And if I come in, they shrink. That's what these circles are. But as I get to the horizon, these circles begin to stop changing size, and they stay at charge at radius q. those are the S2s. This is just a cartoon, so I could draw it on the page. And so you end up with this ADS2 plus S2 as they go near the horizon. So that's the kind of space-time we want to study. We can at least study the physics near the horizon, and we're going to study it at low temperatures where we should be able to then look at the quantum dynamics of the system and see if we can see what happens. And we'll be focusing on the analog of the spectrum of the system in a moment. Let me say a little bit more about this space-time. What's ADS2 if you've not met it before? Well, a lot of this is a physics colloquium, and I think certainly when I was a student, physicists and others of the physics-like persuasion were fans of Escher and would have posters up on their walls. If people still do that now, maybe you'll have seen things like that. There's tessellations of Escher. And those are indeed nice examples. If I Euclideanize ADS2, for example, it is indeed, it can be written as the hyperbolic plane. And you'll have noted properties. For example, if I take a particular distance there and measure how many fish it is across near the middle, I get a different answer if I'm further out. There's more fish. That tells me that lengths diverge as I move. They get bigger, and in fact, they diverge at the boundary a finite distance away. So that's sort of interesting. And so that tells me, now I do my Gibbons-Hawking thing, which is to say that this should tell me about the temperature. And indeed, if this is the boundary at the edge, it's of infinite length. Beta is infinite, so T is 0. So this is indeed the T equals 0 limit of the black hole. We really want to study finite temperature. And what that turns out to be, and that was worked out when people started looking at this sort of problem again, going back to people like Hirai and Polchinski, is the realization that you need to bring the boundary in a little bit. So you have ADS, the blue stuff, that's where the gravity is, and then you have some green boundary, which is of length beta. But when you do the arithmetic, and the model, the reduced model to 2 dimensions that people use that captures all of this, at least in a limit, is what's called JT gravity. And what you see is that indeed you have dynamics on the boundary. It can take any shape it wants as long as it's of length beta. So that's the model I want to study. JT gravity, the thing I get by reducing this problem to 2 dimensions, I have this sphere of some size, which is set by the charge of the extremal black hole, has some entropy. I'm going to call the extremal entropy S0. And then I dimensionally reduce. I get a term that looks like this, multiplying the Einstein-Hilbert term that you'd normally write down in gravity. I have a scalar that represents how much that sphere has deviated at finite temperature away from the size S0. That multiplies a piece involving the Ricci scalar plus 2. And then there's a boundary piece that involves an extrinsic curvature term as well. That's the boundary value of this scalar. This linear appearance here tells me that the equations of motion of the scalar simply enforce that R is -2. It's a hyperbolic geometry, just as we already knew from the previous slide. So in the bulk, it's ADS, but then the dynamics all ends up being on the boundary, and it turns out to satisfy an action that's called the Schwarzian action. It's a simple action with some very beautiful properties that tells you what governs the shape of this boundary. And I'm not going to go into the details of what it is. You just need to know that it exists. You can work it out. In fact, you could actually, it's not too hard to compute this extrinsic curvature term and see it come out. There's an additional piece here, which is the Einstein-Hilbert term, which, as you may know, in 2 dimensions, there's no dynamics for gravity on its own. So the Einstein-Hilbert term simply counts topology. So if I put this not just on disk topology, but any topology, call it some manifold M, this S0 will just multiply whatever 2 minus 2 times the number of handles minus the number of boundaries is the Euler character of the surface. We'll see it'll give us a nice counting parameter in a moment. So the boundary dynamics gives me the Schwarzian action essentially this looks, at least at leading order that we're working at, as though I've decomposed the thing into just a simple boundary problem, 1 plus 0 dimensional problem, as a result of doing this 1 plus 1 dimensional problem. I'll comment about why this isn't the answer to the holographic search for the non-gravitational theory that we want to be dual to this two-dimensional gravitational theory, although people for a while thought it might be. So on the topology of the disk, you can do this computation. It looks like this. And you can write the result, some function of beta, as the Laplace transform of some spectral density that I will show you explicitly, because I'm going to talk about not just it, but an infinite family of corrections to it in a moment. Somewhat annoyingly, the parameter e to the s naught, or 1 over e to the s naught, is called h bar. It is not the h bar that I have set to 1 for the 4-dimensional space-time quantum h bar of Planck. Although, if I have time, I'll show you that it actually is the h bar of an auxiliary quantum mechanics that helps do computations. But don't confuse them. What you can see, I'll say in the next on the next slide. So, and those are some of the authors that completed this piece of the puzzle. Okay, how am I doing on time? Good. So this expansion parameter is going to be important. Remember, S naught multiplies topology, multiplies the order character, and that'll come out. Some power of this e to the S naught will come out multiplying whatever order I compute at if I compute on manifolds of higher topology. And this was a really nice observation that led to something I'll talk about in the next slide. But let's have a look. If we were to work on manifolds of the topology, and you might ask, why are we doing that? And you might answer, well, I'm doing quantum gravity, so you can't stop me. Then you would get a perturbation series like this. This was the leading answer. And I plotted it for you. It's something that grows, some sort of density of states that grows exponentially because of that cinch. And then there are corrections. I haven't written those down for you, but those are also functions of E that can be computed. One of the beautiful things about this subject is that you can actually do the path integral honestly on the gravity side, and then compare it to something, and I'll show you what to compare it to in a moment. Very importantly is this beyond piece. So there might be, and there will be, physics beyond just this perturbation series, non-perturbative physics. And a lot of my work has been involved in asking, what does that look like and what does it teach you? So I'll tell you about that in a moment. Generally, then, we might expect that we have the partition function looks like some series in powers of h bar, functions of E or functions of beta, plus non-perturbative corrections. So the landmark result that I'm going to talk about next by Sarge, Schenker, and Stanford was the remarkable discovery that if I do work on some manifold, some arbitrary manifold, that the path integral on any manifold M, which remember comes with a factor of e to the s times the Euler number of that manifold, is equivalent to the double-scaled large n a double-scaled large n random matrix model. There's an expansion parameter in 1 over n, and 1 over n to the minus chi. If I compute at that order the right thing, which turns out to be essentially insert trace of e to the beta m into this matrix model in the way I'll show you in a moment, the answers you get from doing that actually match the gravity result. So what is that? Well, matrix models have a very long and beautiful history that, again, that's a whole other talk going back to Wishart and Wigner in the early part of last century, applied to a variety of interesting problems. And it's a rich field that shows up in condensed matter and disordered systems and many other areas. the gravity people's take on it goes back to Tufte in the early 70s, where for gauge theories, he was interested in asking what happens if I expand the some SUN gauge theory in large N, and then look at the 1 over N corrections. And he noticed that the Feynman diagrams, and same is true for these simpler models, the Feynman diagrams order themselves in powers of 1 over N, according to what surface you can draw the Feynman diagram on. So at leading order, all the Feynman diagrams you can draw can be drawn on the plane or the sphere. At the next order, they can be drawn only on the torus, and then the double torus, etc., etc. At the same time, there's something else going on. You could actually you could actually decorate these Feynman diagrams in the way I've done here, seeing that they're dual to tessellations of that same surface you've drawn the Feynman diagrams on. Summing over all possible Feynman diagrams, as you must to compute the integral in this way, would then be equivalent to summing over all possible tessellations of the surface of that topology. Well, that's exactly what you would need if you were trying to do a discretized sum of the path integral, which is sometimes hard to do using continuum methods. You can get smooth surfaces out of that by tuning various couplings in the potential of the matrix model to certain critical values where the universal physics that comes out is such that the effective size of these triangles is 0 compared to the area of the surface you're trying to tessellate. And if you tune to those critical values at the same time as taking n to infinity, that's called the double scaling limit, you'll get a model that captures some model of two-dimensional gravity. And what Saad, Schenker, and Stanford showed is that that set of techniques, which has been around since the late 80s and early 90s for other kinds of gravity models, is exactly what you need here to define the full JT path integral. But I should say it's perturbative. It uses some beautiful properties of the mathematics that underlies it that have been worked out by Mirzakhani and turned into matrix model language by Enyard and Orentin to show that, in fact, you don't actually explicitly need to know the matrix model potential, which is in principle a hard problem for this kind of problem. But what you can do is you can work out the results of having the answer at one topology. You can work out the result for the next topology using certain kinds of recursion relations that you can derive from the matrix model. And in that way, they showed that if the disk order, which you can compute using other methods, has this spectral density, I can compute all the corrections at higher order to the spectral density by an iterative procedure based on this beautiful mathematics. And so it was that got people extremely excited about some new ideas concerning this result that I'll tell you about on the next slide. A very important thing to mention is that there are classifications and generalizations to other kinds of JT gravity that Stanford and Witten developed a couple of months later. Non-perturbative physics is going to be extremely important, and I should say that there are some important non-perturbative insights in those papers that sort of start showing some of the features you'd see from a non-perturbative story. But as I'll show you, they only scratch the surface of what you can see if you use fully non-perturbative methods to understand that. And that's the sort of thing I've been working on recently. Let me say a little bit more about the matrix model approach. So that spectral density, you can think of it in the following way. So, well, I already explained this. Here's a couple of diagrams. You can actually do this if you get bored with what I say for the rest of the talk. Just copy this down, keep that n, that's important, work out some Feynman rules and start drawing diagrams. You'll draw this, you'll draw that. If you work out the powers of n, you'll see you have n to the 0, n squared. Why do I have a ribbon here? I have a ribbon here because a matrix has two indices, and you've got to keep the integrity of the index structure in the Feynman diagrams. So if you have index I and j, you can think of one side of the ribbon as I and the other j, and then it all propagates nicely. So breaking the ribbons to put things on topology that don't belong would mess up the whole structure. So you can't put this on a sphere for that reason, but look, it'll go on a torus and so on and so forth. What you end up doing is working in terms of eigenvalues of the matrix model. You diagonalize the matrix with the unitary because you have this nice trace that allows you to do that. And you get a Jacobian for doing that called the van der Mon determinant that looks like this. And then you have some one-dimensional problem, the line lambda, where you have the lambda i's of the various eigenvalues, n of them. And it's what's called the Dyson gas in the old language. You can see, and unfortunately my pencil isn't working here, so I can't draw the diagram I intended to, but you can imagine that there's an attractive piece coming from the potential, right, some quartic type thing. And so that's trying to push them toward the middle if I had it centered here. But this repulsion term, if you exponentiate this, it looks like a logarithmic repulsion, makes them want to spread out. And the result of that competition is that it spreads out into some sort of droplet. It turns out then the double scaling limit, where you get the universal physics, all comes from what those endpoints are doing as n goes large. So you blow up this region. So lambda is an endpoint value plus a little bit e. And then you look at the spectral density as a function of e, and that's what you get. So that's what we're trying to solve for in general. And that leading piece, that cinch function that came from the Schwartzian, studying the Rising-Norsham black hole semi-classically, is what you got. And then you have an infinite family of these topological corrections that I told you about. But there's more, remember, right? This beyond. So what is going on in this in the beyond, as it were? So we need a non-perturbative formulation. So again, there's a beautiful history and a whole bunch of techniques that deserve more than one slide, and we don't have time. So I'm just going to give you a flavor of how that looks. And what people tend to do is they write the matrix model now in this lambda basis where it's some problem on the line. You can decompose everything in terms of language that you may have seen used elsewhere. Families of orthogonal polynomials, just in the same way we use interesting families of orthogonal polynomials as a basis for, eigenfunctions of the hydrogen atom or what have you, of the harmonic oscillator. You can do the same kind of thing here. The family of orthogonal polynomials, Pn of lambda. Sorry, I can't write it. They're normalized such that Pn of lambda goes like lambda to the n plus lower powers. And there's some orthogonality condition that's like this with respect to the measure of the model itself. And there's that's just some normalization. They're orthogonal, not orthonormal. So you can make them orthonormal by dividing by root h if you want. Doesn't matter. Well, they obey a recursion relation. Given what I just told you about the PNs, you can see if I multiply lambda by Pn, I'll get Pn plus 1 plus some noise to lower orders. And for an even potential, it actually turns out to be fairly simple. It's actually just Pn plus 1 times some coefficient I'll call Rn. So actually, you can rephrase the entire problem. All matrix integrals can be boiled down to this kind of integral with powers of lambda inserted in there. I ask for the expectation value of some powers of the matrix. That turns out some function of the matrix. It turns out to be some function of the lambdas. It'll be an integral like this. I can then use these recursion relations to actually decompose this and then use orthogonality and get answers. That's essentially how it works. So all I need to know is the orthogonal polynomials for a given potential, and their recursion relations will tell me about all of them, and that defines the whole problem. So that was before I took any double scaling limit. So everything can be determined by the PNs and the RNs. When I do the large N limit, that index on the PNs becomes a smooth variable I'll call X. Lambda, remember, spits out a piece, that scaled piece I want called E. These things then end up being functions, psi, and this a function U of X. And going a little bit further, what actually happens when you examine that whole process of computing everything in terms of these orthogonality relations, they look like brackets in some kind of quantum mechanics problem. The Hamiltonian for that quantum mechanics problem has as eigenvectors the psi's themselves, the orthogonal polynomials, up to some factors. with energy E. And that potential, that thing that tells you what all the orthogonal polynomials are, is a potential for that Hamiltonian. And that H bar we talked about previously actually ends up being the H bar of that quantum mechanics. So this is how you work. If you can, knowing the potential completely, not just perturbatively, involves figuring out what this U is fully to all orders in this H bar parameter, then you solve this spectral problem, and then you can compute things like the partition function for that boundary with length beta turns out to be this expectation value inserted in there. It's some funny looking integral, but it has meaning in the matrix model. It's a funny thing to do from the point of view of the quantum mechanics, but you can do it. And you can get things like the spectral density out exactly in terms of this, this spectral problem. So this is the tool that I use in a series of papers to show how you can fully characterize not just the perturbative result, not just do the perturbative results, beautiful as they are, from Triple S and Charles-Schenker Stanford and Stanford and Witten, but you can complete those stories non-perturbatively as well. So with this a year ago, or even less than a year ago, that would have been, I would have shown you all those results and we would have ended with that, but I want to go even further than that because of recent results. But this is essentially the story then. Take JT gravity. For reasons that I don't have time to go into, you have to solve some horrible nonlinear high order differential equation to solve you. It ends up being a numerical problem, but it's okay. You can solve it, and you can get the size and the e's, and then you can compute those spectral densities. So there, this dotted line is that cinch function that we talked about before, the leading order. And getting those perturbative corrections is something that's happening at large E. It's sort of large E compared to H bar, if you like. And that'll sort of do some corrections up there. But to get deep into this region where you see these wiggles begin to appear, you need the full non-perturbative story. Now, this is usually where we stop in gravity. When we say we've done the full non-perturbative story, even if we even get this far for JT. But in other similar similar problems, this is where we usually stop. We get those wiggles, and we say some correct words about underlying discrete structure, et cetera, and they teach us things about important quantities, knowing about this form of the non-perturbative corrections, and then we're sort of done. But actually, what I've been realizing in recent times is that it's just the beginning. Because you can then go and ask, what's the origin of these bumps? What do they actually mean? And not only can you find out what meaning they have, once you see where they come from, it changes everything. So in the last short time, I will show you where they come from. And I will offer some meaning for them. So the current prevailing view is that actually the big exciting realization of this result of Triple S is that JT gravity is this ADS2 gravity at finite temperature, that's what that tilde means, so deformed away from pure ADS2, is dual to some random matrix ensemble. And that was a big surprise because, of course, we started out looking for something that had a definite Hamiltonian, some dual problem that was something like a Yang-Mills series has a definite, this definite Hamiltonian, not an ensemble of things. But a random matrix model is an ensemble, and it seems to capture the JT gravity. And so this has led to a lot of puzzles about, well, is gravity an ensemble fundamentally in all dimensions? What could that possibly mean? How do we make sense of that in higher dimensions where ADS-CFT has already told us, it would seem, that it isn't an ensemble. And in fact, if you work it through, you'll see that you run into problems. Gravity, in view of the time, maybe I won't go through this in great detail, but gravity as an ensemble runs you into telling you that the duals that you thought were available and that we understood very well since ADS-CFT appeared in 1997 don't factorize. You take two copies of the partition function and try and compute a correlator, and through the kind of diagrams I drew, you have contributions like this, which are factorized, We also have these wormhole contributions, which would tell you that somehow you're getting contributions from the ensemble. We interpret it that way, and that's telling you that in fact your theory is not defined in terms of a single Hamiltonian. It's very puzzling. And so people are talking a lot very excitedly about gravity being an ensemble, and they're either trying to fix what we've done in all dimensions and make that consistent with that, or they're going down back to the matrix model and saying, well, maybe we need to somehow keep the ensemble aspect because it gave us gravity, but somehow turn it off because the ensemble part is spoiling factorization. So it's led sort of, I wouldn't say a paradox per se, but it certainly led to some very sharp tension between things that we already know. And as I already said, the physics of the Schwarzian isn't good enough to be the holographic dual. The key point being that the continuous spectrum that I've been showing you means that there isn't a sensible Hilbert space. I need, as we already know from the black hole perspective, I need something that's discrete. When the matrix model came along, people were already puzzling over that, and they realized, oh, wait a minute. The random matrix model is exactly what we need because it has a continuous spectrum, even after you include all those corrections, as I showed you. And so fundamentally, the fact that the Schwarzian, fully corrected in this way, has a continuous spectrum is consistent with it being a random matrix model, with it being an ensemble instead of a definite Hamiltonian. Also, there's been beautiful work on the correspondence between black holes and chaos, and black holes as chaotic dynamic systems. And various parts of the literature of quantum chaos already point to random matrix statistics as being sort of an earmark of quantum chaotic behavior. So it's quite understandable at this time, 2019 or so, when this correspondence to the matrix model came along, that that was the right thing to say, that these two things are equivalent. Well, today, and this is where I should give you a health warning. This is potentially controversial. I would like to show you why I think this is too hasty. And actually, while an understandable identification was made, there was a major feature that was not expected that I can actually show you that the matrix model points to, telling you that you can reconcile all these things. And the answer will be that there's no factorization puzzle, it solves it. And indeed, there exists precisely the kinds of Hamiltonians that you need to be a holographic dual. And in case I don't get to the end, let me tell you that the matrix model itself can point to the existence of spectra of Hamiltonians that become this at large energy compared to h bar small. But if you study properly the non-perturbative physics, you'll see that at small energies, deep in the regime where you should see the discretization show up, it indeed does become discrete. But it does it in a very smart and subtle way, because matrix models are smarter than all of us, and you have to, they continually produce wonderful surprises. You have to read them correctly. And I think that's what we collectively as a field have not been doing, which is interpreting. So let me show you in the last, and I think I started a little late, so 5 minutes. Good. So I'm gonna borrow that time back. I'm going to show you some cracks, if you like, in what I think is the current paradigm. So let's look at some roots of finding the holographic dual, and let's remember that in analogy to all of the rest of ADS CFT, we don't just consider the ADS factor; we also consider the spherical piece that it came with. That's where the full quantum gravity actually is. Let me just remark that prior to 1997, for the experts, no amount of messing around with quantum gravity in ADS5 on its own would have ever told you that there was a Yang-Mills dual. You had to learn about the full theory as a 10-dimensional theory with an S5 piece, and then learn about branes, et cetera, et cetera. So the analog is, I think that's a lesson to what we're doing here as well. So you have the ADS5, ADS2 cross S2, stay 4-dimensional. I have that leading Schwarzian piece which came at h bar to the -1 times the sphere. And then I'd like to work out some corrections plus beyond. And what is the answer? Is there a holographic door? Or you can take the two-dimensional route, which looks like this. You can reduce like this. You go down to JT gravity, where now the S2 has gone away, and the radius of that S2 then ends up multiplying this topological term, and we did the topological expansion that we talked about. There's no topology up here, and that's a clue. There's no topology in the actual upper root. This was a nice device which came about from that dimensional reduction and gave us something that's beautiful and true, but as I'm going to tell you in a moment, I think we misinterpreted it. And in fact, the key to understanding the misinterpretation is to look back in our history of the physics of the tools we've been using. So WWWD, what would Wigner do? Right. So let's go now. I want to solve this problem. It's hard. I want to find a Hamiltonian, a large Hamiltonian, right? N by N Hamiltonian. That's hard to solve. How do I do that? What would Wigner do? Wigner would go, well, I'm gonna do my best. I'm going to try and characterize it as much as possible. And for us, that means at large E, its spectral density looks like the Schwarzian. And then I'm going to study the ensemble of such H's and see if the ensemble can teach me some of the typical properties of that matrix. This is exactly what Wigner did, as you may recall, for nuclear physics. And in fact, what Wishart before him did in 1928 for various other models, which lay outside physics, so we tend to forget about Wishart. Let's just check parameters. Well, the entropy is telling me what the size of the matrix should be in this problem. So the expansion, the 1 over n expansion parameter should indeed be e to the minus s. And of course, that's exactly the expansion parameter in the triple S matrix model. And it just so happens that that's exactly the expansion in topology in JT gravity when I reduce to 2 dimensions. But I must remind you that the 4-dimensional route doesn't really care about that topology. It doesn't organize things in that topological expansion. So Wigner would do this matrix model and extract the typical properties in the way that I showed. He would not then stop and go that nuclear physics, a nucleus is an ensemble. He would not, if we look at our disordered systems colleagues in condensed matter, that sample on their lab is hard to study, and so they use ensemble techniques. But at the end of the day, they come out of the ensemble. And I think the same thing should happen here. We must look at the actual matrix model. Now you see why it showed up. It actually showed up not because it's the answer, but it is indeed, by the 2 routes I showed you, it's the nice expansion that showed up to tell you how to do things the Wignerian way. So what we need to do is actually study matrices. And so in the last few minutes, I will show you, and I think I just need 3 more minutes or so, I will show you what you do. Let's remember, these are just matrices. It can't be that hard. So let's do something you can try at home or code it up on your phones right now. Let's just do what Wigner did. It's a random matrix. Now we're just Gaussian probability. So this is easy to code up. Compute, every time you get one, generate it with that probability, compute the histogram of its eigenvalues. And as you know, because you probably did this in some class, you get the famous Wigner semicircle law. And if you zoomed in the way that we would to do gravity, you get something a little bit more detailed. You get e to the half, right? That's the remnant of the semicircular law here. That's that dotted line. But then you actually see that there's some structure. That's the analog of those non-perturbative wiggles that I showed you how to compute for JT gravity. And as I said, that's where we usually stop when we use random matrix models in gravity. We should continue. In this case, you can solve this exactly. It's called the Airy model, but you don't need that. Let's carry on. Let's run the problem again, but before we do anything, every time I get an eigenvalue, I ask, was it the first or the second or the third or the fourth of the spectrum? And then histogram on that. Maybe color code to make it look a bit fancy, and you'll get that. And it's sort of amusing to me because when I began to go around to my matrix model colleagues and show them this, they had no idea what this is, and neither did I, right? The rest of the field that use random matrix models, but not for gravity, in other fields, focus precisely on this sort of thing. This is what interests them, the statistics of the eigenvalues themselves. This first one is, in fact, what's called the Tracy distribution. It's extremely important in a wide variety of physics, telling you about new kinds of universal behavior, and you can compute these peaks individually. Let's see what's going on with those peaks. You can see that they're actually, well, they're telling you about the individual energy level statistics. This is the statistics of the first level, the second level, the third level of the spectral problem. As you go to higher energy, which is going toward perturbation theory in the language we've been using, these peaks get narrower and they in fact get closer together and they form a continuum. And in the limit, these will reconstruct the root E leading result. The analog of this for gravity is that this will be the Schwarzian. So the matrix model is doing something very subtle here. Yes, there's a continuous spectrum, and that's what we've been identifying as the JT in the gravity version of this, as the JT spectral density. But actually, and this is not speculative, this is a mathematical result, you can show that it's also a sum of a discrete spectrum. But the spectrum has been broadened by being inserted into an ensemble. So there's an energy associated with each of these peaks, which is a discrete spectrum that then merges into a continuous spectrum at high enough energies and becomes the Schwarzian. So there's some beautiful techniques using Fredholm determinants, etc., that are well known in the matrix model literature that I've brought over to this problem. And I can use them because they are built using the actual eigenfunctions that I've already computed to get those wiggles. Those same ones can get you a lot more. There's a kernel you build, which looks like this. And then this kernel goes into an integral operator whose determinant you can compute and get various things out. I wish if I had another 5 minutes, I would tell you how that works. But let me just entice you with something interesting here. This is something which exists in the matrix model, regardless of interpretation. It's just there. And it controls things like 2-point correlators and higher point correlators, which turn out to be slices of this thing. The diagonal, you can see, is the actual spectral density. This is the sort of thing that's used, but only slices thereof, or the diagonal. But you can see it has so much more interesting physics that we haven't been using in the gravity community. And it's this physics that, when you put it together in the right way, gives you those peaks. So in view of the time, I'm going to jump to the end, tell you how it works, and some beautiful techniques due to Bornemann that help you examine it. But here's the answer. There's the Schwarzian. There is the full non-perturbative answer that you can define in a non-perturbative definition along the lines I told you with the wiggles, which is where we usually stop. And then there are the underlying peaks that you can compute using these techniques. So this is what I think is going on. I think what we have undeniably is an underlying spectrum. If you associate either by the most frequent or the average an energy with each of these peaks, you get something that is a spectrum that is discrete, that at large energy compared to h bar, the classical limit, becomes continuous and becomes the Schwarzian. That's exactly what we were looking for in 2019, before the matrix model came along. If we knew about things like that then, we would have said those were the holographic dual. But the matrix model came along, and we quite understandably, for the reasons I told you, as a field, we took the whole thing to be the dual. And so the proposal is that rho isn't the spectral density, but these E's associated to those peaks is the spectrum. And then you see what the Wignerian perspective tells you. I had this root. I want to know the answer. The matrix model root, although I think we misidentified what it is, it does still turn out to be an incredibly powerful tool, because it tells you in a Wignerian way about these peaks, and then you read off the spectrum at the end. So that then is the answer. That is the holographic dual of ADS2 cross S2, and we're done, right? We've seen a lot of exciting progress then. It's crucial to not just use the Tuftian approach that we normally use with matrix models, but also have the Wignerian approach. And I've given you an argument as to why the Wignerian approach is in fact what is going on, because that higher dimensional root doesn't in fact know anything about that expansion into topology. This then sheds new light on not just this, but many other gravity approaches using random matrix models. And then holography in 2D quantum gravity then looks like holography in all the other dimensions. There's no factorization problem, that puzzle goes away. And then, very excitingly, we actually have the quantum spectrum, or at least a good draft, very, very near final draft, if you like, in the simple case of what the black hole spectrum looks like. That spacing is E to the minus S0, which is exactly what a finite entropy should tell you should have in looking at the dimension of the Hilbert space. So thank you very much for listening. I hope you find that interesting enough, at least to look at the paper. And of course, whether you agree with my interpretation or not, there's so many interesting things going on that I think you might find it interesting to dip your toe into this area and get involved if you like. So thank you.
Thank you for the talk. Clifford, you also probably can see if there is someone asking questions online.
Oh, okay.
And we have also a question from the floor from Ethan.
So if I may have a quick question. So can I understand these individual distributions, this P label by N, as describing the KK modes coming from the four-dimensional quantum graph to reduce IS2?
As coming from
the KK modes, the closed Klein modes coming from the metric degree rhythm reduced IS2.
No, they aren't the Kaluza-Klein modes. At least as far as I think about it, there's certainly no in that reduction. The Kaluza-Klein modes were not included. What you have instead is a story which I didn't have time to go into, where you see, in fact, the spectrum, and then you have the ensemble of all the other spectra that are similar to it. And then what the matrix model does, it smears them all together and makes these peaks. So you might ask then, what does that mean from the point of view of the reduced model? And the other output of this set of ideas, at least my take on it, is that that's exactly what topology is. Now we know what, not as perturbatively, but non-perturbatively, at least in this nice example, what it means to put quantum gravity on other topologies. Again, let's go back to ADS-CFT in all dimensions. We got Yang-Mills on a simple space-time with just the boundary. And then, sorry, not Yang-Mills, ADS5. And then we saw that was Yang-Mills. After that, we then put that on interesting topologies, for example, black holes, and we saw that it's the Yang-Mills theory in a different phase. So the spectrum has been adjusted somewhat. So that's what's going on down here as well. Different topologies are telling you about the spectrum of that one theory after you've done some deformation. And in fact, there's some papers from last year by Maxfield and Turiachi and by Witten that showed, hey, if you look at deformations of JT gravity, you can write those as matrix models too. And they showed how to do that in perturbation theory. And with Felipe Rousseau, I showed, yes, you can use my techniques to turn that into a fully non-perturbative story as well and see what happens to the full story. Now I realize what that means in this new picture is that simply tickling the black hole moving is equivalent to changing phi, those deformations. And that essentially allows the theory to scan those peaks through and pick out different spectra. And so now we see that the matrix model statistics that should organize the deformation, should organize tickling the black hole horizon, etc., is there. And that's what the matrix model does describe. And it does it by mixing the spectra in this way. And it's described all the answers to arbitrary orders as a matrix model. So it's a recasting of all of these things that we've understood in this other perspective, in this framework, showing that we're not losing anything. I always try and tell people about about this, that I'm not trying to take away your matrix model toys. I love them too, but I'm showing you that they have new features that we haven't thought of, and so that's sort of how to think about that.
Right. I guess the key point I want to get is that I understand what you're saying, but can you infer from these peaks the information about the spectrum of the original Hamiltonian, something more precise?
Yes, I show you. So you remember, it's telling you about the typical behavior. So for example, a very good thing you can get from these peaks would be, well, what is the most favored energy at first level? So that would be the peak. Or it might be, and I'm still working on which it is, it might be that it's what's the average energy of the first level, of the second. Both of those seem good right now. I'd like something, I have reasons to think it might actually be one when I wake up out of bed with one set of thoughts, and then the next morning I have reasons for it to be the other. But there's a precise thing one can say in some simple models that suggests that it's the peak that might be the most interesting and maybe the answer. I could tell you more about that if you like.
Yeah, so astrophysical black holes, right? So they're, as you mentioned, Kerr black holes, they're rotating, but they're not charged. So I just want to make sure, would that apply to those two? Because you had the example of the charged.
Indeed. So we focus on the charged black hole. The key point here, I think, was the actual extremal limit itself. The fact that you have an extremal limit, you get these nice exactly solvable models that come out. Now, something like something like these kinds of dilaton sort of scalar plus two-dimensional gravity type models can come out from Kerr as well, at least as a subsector. It seems that there are other pieces as well, but it might be that the essential part of the story we're interested in is indeed again captured by this sort of thing. And so the key role here seems to be the fact that you have these simplified spacetimes that emerge when you're at or near the extremal limit, and then you can actually do calculations. So that's why I find this exciting, that although it won't be exactly the same story for Kerr, I think it'll be somewhat similar, and I hope, and that's cool because Kerr's in the sky, so that would be nice. Although, oh yes, and then of course the other thing is that arguably a large fraction of them are somewhat close to extremality, so that's kind of interesting too. Yeah.
So there is a question, I think, from the remote audience.
There's a question.
Yes, I have a question.
Mm-hmm.
Yes, can you hear me?
Yes.
Yeah. So the question is, ordinarily, when you quantize, say, the black hole, you would get a discrete spectrum. You would get, instead of the rho E, you would get a series over delta functions centered on some energies, right?
Yes.
So the question is, when you say that for a specific energy you have a certain distribution, what is it that you exactly mean?
Well, I'm saying actually that the distribution is simply pointing you to a specific energy. So you should replace the actual answer replaces those distributions by specific energies, delta functions, if you like. So the ensemble interpretation, taking the full ensemble as the answer, keeps those distributions, and then you have to do a song and dance about what that means about a specific black hole. In my opinion, it's actually much simpler. And it's just saying that this was a Wignerian approach to getting the answer. The matrix model can't take you all the way to the discrete spectrum, but it can point very, very definitely to it. And the answer is that The energy for the first level, for example, is more than likely going to be near the peak of the distribution and highly unlikely to be, much further away from that. And so that's a definite energy. That's what we do in all of the rest of physics. So we should do that here, is what I'm saying. So in some sense, I'm being controversial by being conventional.
Yeah, so in order to get the discrete spectrum, what extra thing should you need to do?
Well, ideally, you should solve the problem exactly. You should do the full quantum gravity theory. And so embed ADS2 cross S2 in some string theory and build a family of brane models that probably has as its near horizon geometry some quantum mechanics that you then solve the spectrum for. And the prediction is that that would be the answer. The matrix model does its best, and I think rather beautifully, and I think this is why this triple S approach is such a landmark, because it's telling us we can use matrix models to characterize the answer in the spirit of Wigner without necessarily having the full tools available.
Yes, so there's a question there.
Yeah, so just to add to your point, from the condensed matter perspective, which I guess I am, this is all super conventional, right? Because no one would have made that mistake of ever interpreting this average as being real, but basically as just giving you the prediction of some average ensemble. So now the question kind of is, you compute essentially to all orders in 1/n the density. But also in condensed matter, we're almost never interested in the spectral density rho of E, because in condensed matter, this is highly non-universal. It depends exactly on the problem you look at. So almost always you scale that out. And actually the thing you're interested in is in the correlations between the levels.
Yeah.
Because those give you the universal physics.
Yeah.
So my question to you is, in gravity, what is it that we would be seeing that is caused by the correlation between the levels in this random matrix theory? Because that's the universal.
That's a great question. Well, so I should say, yes, that is a universal thing, but it is still important to know what the actual answer is.
Right. Sure.
So knowing the spectrum is important.
Right, sure.
But something that actually guided the random matrix model people that I mentioned, Sarchenko, Stanford, etc., was indeed precisely things like the spectral form factor.
Exactly.
Yeah. And so that's what topology is doing. When you look at the spectral form factor, it's in principle, it's a messy thing. But as you know, if you then do the ensemble average, you get universal features coming out. So the ensemble average washes out all of the sort of oscillations you get due to the spectrum and gives you the ramp and the plateau. And that is what the matrix model computes beautifully. It uses that full row now, correlations between that, to compute a smooth function, which is the average of those things. And then when you convert it into a gravity question, it's that wormhole geometry I drew.
Right.
So the growth of wormhole geometries, building you higher topologies, is what you get from asking questions about ensemble averaging over the whole spectrum. But we still need to know the answer to what is the holographic dual. So we need to also know the spectrum. And I think what we with respect to all this wonderful work that was done, and I mean this collectively as a field, I think we got seduced by how well the matrix model does that, and by the fact that also in this case in 2 dimensions you get the sum over topologies, and they all seem to fit together nicely. And we called the whole sum over topologies gravity, as we sometimes do. And then we said, well, what is that? It's the matrix model. But both things can be true, and but you have to be careful. And the answer, the full gravity answer without topology, needs to have an answer, and that is the full spectrum I told you about. I hope that makes some sense.
Yeah, I think it does make sense. I guess I was more wondering this correlation hole, for example, that you see in the spectral form factor. It's basically the fact that after some amount of time, which is dual to energy, you get things which you would normally conceive as being independent are actually anti-correlated.
Mhm.
And so I was wondering, what does that mean? Does it mean that different topologies are anti-correlated, or different dynamical spacetimes are anti-correlated?
No, good. The topologies are the sort of sum total of all of that once you've averaged over everything. So they don't tell you about a particular spectrum anymore. They tell you about the ensemble of spectra. And I think that's where we made our quote unquote mistake, because we like smooth things.
Right.
In gravity, and so we took the smooth things to dominate how we interpret everything, and but the smooth things can only tell you about ensembles over the spectra. But a real system with a real spectrum has messy noise due to correlations between those spectra producing wiggles in the form factor, and so we need to know what that spectrum is to finish the story.
Right.
Yeah. So that's that sort of thing. So it's subtle, but it's important, because I think we're chasing after this interesting question about whether gravity is an ensemble and what happens to factorization. And I think those are interesting questions, but I think they were not well motivated by that interpretation that we started with.
Can I ask a follow? I know you've been talking a long time. If you want to stop.
No, it's okay. I can take a couple more questions.
It just seems like to me that the when you randomly sample the matrices, you get a bunch of eigenvalues. You can order them. You can histogram. You can study all the correlations and all the things. And the roughly the idea that's a discrete spectrum, and somehow like the solution you're looking for is kind of in some sense corresponds to like a sample from that
it's a sample.
And so,
but it's a typical sample.
Sure, but then if you ask like, what does the randomness in the matrix model correspond to? It seems to me that it corresponds to the deformations that you're doing to ADS and how you didn't go. I don't know if that's exactly right, but it seems like if you want like the solution, it seems like it's going to be very dependent on like how you take some sort of limit, are you getting rid of the deformation? And when you say the solution, is there no more deformation anymore?
No, I'm saying that the solution comes with its deformations. When I start deforming, then I start deforming the Hamiltonian.
Sure,
but before I deform, I have the Hamiltonian.
Right.
So what is it?
But so for any particular deformation seems like it has a solution with some particular spectra.
Indeed.
And that's like the random matrix model basically doing that. So, but when you're saying you're searching for the solution to where you're going to have a particular like well-defined. It seems like it's not referring to any particular deformation.
Well, I could ask the same question in field theory, right? So I can ask you, what is the Hamiltonian of, some of the Young-Mills theory I wrote down?
Sure.
Yeah. And that has an answer, you agree? Good. Now I can add in a term that deforms it a little bit, and that'll have a different answer.
Right. Yeah. So then
it's the same thing.
Yeah. Okay. That's fine. To me, if you do that, like it seems not super obvious to me how that's going to correspond to anything in particular about like what the random draw out of the from this matrix perspective is going to do. It's a very particular limit, right? So the peaks of distributions aren't very well defined. Like if you change from energy to something else, the mode is not invariant, the mean's not invariant. Like all those things are not very well defined. Expectations of correlators, those are all well defined. So it's not really clear to me that like the spectrum is going to be well defined by any kind of mean or average of the individual peaks in that sense.
Well, the matrix model does the best that it can.
No, for sure. I'm just thinking about like conceptually what would like it seems. There's some chance that it's like you take everything like 100 sigma to the left of each of those distributions, and like if the solution is a spectrum that's like everything's way super duper unlikely.
Well, no, that's going a little further than what we know absolutely is true. There are many things you can compute in the matrix model. For example, you can compute the average characteristic polynomial is a very natural thing to compute. So that tells you what are the eigenvalues of the average matrix, right? So that's not just sort of
right, but this isn't the average. The solution
let me finish, right? So that's not just some random thing. That's a specific matrix that you're characterizing. It turns out there's a natural object in the matrix model that survives it to the continuum limit that you can build out of these wave functions. And it will then be telling you precisely that. So you look at the zeros of that thing. So you're going to say those zeros don't have meaning then?
No, I mean, I don't know. This
Okay,
is out
good.
of my
So
depth.
the
I'm
answer-
just
so-
trying to,
so-
I think it's fascinating. I'm
So
just
the
trying
answer, I'm giving
Yeah.
you some extra information
Yeah,
here,
yeah.
right? The answer is that those zeros line up with those peaks. They
Okay.
don't quite get the peaks exactly because it turns out to be the n-1 matrix, if you count correctly.
Okay.
This is the n matrix we're interested in. But it tells you that those peaks taken as an ensemble, not an ensemble, as a set of defining a set of energies in some
Right.
well-defined sense is a meaningful quantity. They do not necessarily have a separate. You shouldn't think of them as a completely separate set of entities. Because they're the properties of quantities that remember the matrixness of the whole problem that knows about this set of peaks. And,
Yeah, no, that's interesting.
and so it is, again, I'm not just making this up. This
no,
is
I'm
this
sure.
is something you can
I'm
compute
certainly not
explicitly.
implying that. I'm just thinking.
No, I was
essentially
just saying you were saying that.
Yeah.
It's
I mean,
very important to know
It is
that.
interesting though, that even that though, like in some sense, that there's an answer and then there's some means and then there's a relationship between them.
Mhm,
The fact that they're kind of like, look like they're close by in some sense,
mhm.
it could also be distracting, right? I just mean like
Yeah,
logic,
I know
I just
what you
mean
mean.
like, I mean, what to say? It's sort of like if you have a distribution that has a real mean and you get some number of samples, the sample mean is biased by a little bit, and you can work out some relationship
Mhm.
for how they're related, but the
Uh-huh.
way that they're related will depend on skewness and variance and all
Yep.
sorts of other things, right? So the fact that there is a relationship and generally they're close by
Mhm.
is interesting, but it doesn't necessarily point to the fact that like the sample mean is like necessarily the right conceptual path towards getting to that relationship.
Yeah, I'm not sure I
Yeah.
understood that, but I refer you to the entire matrix model, random matrix
sure.
model literature
Yeah,
for
yeah.
more. And and moreover, the mean skewness and so on and so forth, that varies with E in a way that it also contains information.
Yeah.
I'm not claiming that the matrix model gives you that final spectrum. I'm claiming that in the spirit of Wigner, it's telling you it exists.
Yeah, no, I think it's, I buy your.
Kyle,
right.
maybe let's thank
We should maybe, yeah.
thank Cliff, first
Yeah.
for the intriguing talk.
I think it becomes sort of more clear if you actually think back about this Dyson gas. Because in the end, if all properties can be computed from